All right, picking up where we left off last time, we were talking about prefix multipliers, and we did a brief intro to them. We looked at a lot of prefix multipliers. Again, this is not an exhaustive list. It goes further up, it goes further down for bigger and smaller numbers. We typically are going to be working with prefix multipliers that are within this page. So these are typically the ones that we'll want to know. The really important ones, I would say we really want to know kilo, we really want to know centi, milli, and maybe even micro. But kind of kilo, centi, milli, those are kind of going to be our meat and potatoes. That's what we're going to be using the most, I would say. And for everything else, there's MasterCard. I'm just kidding, it's not MasterCard. MasterCard doesn't work a lot of places. But for everything else, you'll probably just have a table. So like for exam 1, you'll have a table. It'll look similar to this, not exactly the same. It'll have a bunch of the prefix multipliers on it so that you have some time in case you haven't memorized them by Monday of next week, because that's kind of fast. And then we talked about the mitochondria. There's other types of units, not just the basic units that we talked about. There's also derived units. So derived units, derived just meaning it came from somewhere else, and the somewhere else is other units. So we combine some units, put some units together so you can have units while you're doing units. Many of our units of volume are derived units. They're based on 3 dimensions. So any unit of length, like meters, feet, centimeters, inches, any of those units, if you cube it, you multiply it by itself 3 times, like inches times inches times inches, that's cubing it. Then it's now a unit of volume. That would be in raised to the 3 power. That in raised to the 3 power means the same as inches times inches times inches. Other derived units of volume are cubic meters. So the cubic here meaning raised to the 3rd power meters. Cubic centimeters, cubic millimeters, any other cubic length unit. So like cubic feet. Things that are volume units that are not derived, that are not based on other units, include liters and their smaller friend, milliliters. Liters and milliliters are what you'd see on a can of soda, a 2-liter bottle of Coke, or whatever other drinks you might consume. And our reference point, 1 liter, is about the same size as a quart. They're like approximately the same. They're not really that close, depending on how precise you get, but they're roughly the same. If you drink a liter of water, you drink about a liter or about a quart of water. And we'll be using liters and milliliters throughout the course. Any questions about units? So some big takeaways from that slide. Liters are a unit of volume. And we also have a couple of other types anytime we cube a unit of length. So cubic inches, cubic centimeters, stuff like that. Cubic centimeters often also shortened to cc's, especially when you're talking about Mario Kart racing. All right, we're going to now jump into arguably the students' least favorite topic for the entire course, partly because it'll be a constant thorn in your side, like SpongeBob laughing at you every day and night. Significant figures. So the way that we write numbers and the number of numbers that we write out is important. We want to write out the correct number of numbers to show how precise our measurement was. We don't want to write out too many numbers because then it looks like we're measuring it really, really tiny measurements. That's usually not the case. So to give some examples of significant figures, we've got things that have a limited number of significant figures, things that have an infinite number of significant figures. Nickels come in whole numbers. You can either have like integer numbers of nickels. You can have 1, 2, 3, 4, 5. You can count the number of nickels that you have, and there's no dispute about that's how many nickels you have. So like in this picture, those are my nickels. I have those at home. Those 5 nickels, how many nickels do we have? 5. We have 5 nickels. Would anyone like to argue that there's actually more or less than 5 nickels? Is there 5.01 nickels? Is there 4.89 nickels? No, it's exactly 5, right? We can count the number of nickels. It's the same as counting students in the classroom. We have a whole number of students in the classroom. Ideally, assuming everyone's here, that's 32. Nobody would dispute and say, no, there's actually 31.9 students in the classroom. We only have whole students. Come in different sizes, different shapes, but we have the same number of students in the classroom, right? It's always going to be maxed out 32 for this class. So we have exactly 5 nickels. For other things, in this 250 kilogram bar of gold that's in a museum somewhere, in that bar of gold, it's probably not exactly all gold, right? There's some other stuff that's made its way in there. Like if you drink a glass of water, especially if it's out of your tap, it's not all exactly just water. There's some other minerals and things dissolved in there, and you'll see that if you don't like squeegee your shower, if you've got glass walls, you'll see that hard water buildup. That's the other stuff that's in your water. So it's mostly water, it's not entirely water. For our water, we don't really care as much, but talking about 150 kilograms of gold, if this was only 98% gold, that 2% other thing would make a pretty big difference. In this case, this bar is rated to 999.9 thousandths fine gold. So it's really precisely, this is exactly just gold. And so those numbers kind of reflect how accurately, how precisely they measured out the contents of that gold bar. 999.9 is much better than just saying like it's 50% gold. The value of those two would be very different. Other examples of where our numbers can reflect our precision. Scientists, at some point, concluded the average global temperature has risen by 0.7 degrees Celsius since 1880 based on analysis of records from measuring stations all over the world. Thousands of measuring stations, probably millions of data collection points of temperature. And they determined that it's 0.7 degrees Celsius. So there's one number there. The 0 is there just to show us where the decimal is. If we report that value differently, adding zeros, 0.70, that looks a little bit more official, maybe. It looks a little bit more precise. Like, oh, they were pretty accurate with their temperature measurements. If we add more, 0.700 degrees Celsius, then that looks like they measured all the way up to this thousandths place for all of their temperature measurements, for all of these stations across the world, which is not accurate. And if we used the average displayed by the computer, just based on some rough calculations, all of these numbers, that looks like, wow, they really measured that temperature super precisely, and almost nobody is measuring temperature that precisely. So showing it as 0.7 means, it could be 0.68, could be 0.74. It's kind of, there's a little bit of plus or minus that's built into this number. If we add more zeros or if we add more decimal places out, then that shrinks the amount of plus or minus that we have. So like on this 0.70, might be 0.795, might be 0.712. There's a plus or minus still, but it's a much smaller plus or minus. And when we're talking about measurements that we're making in a lab, that we're making for science, we want to have a standard way of reporting those numbers, and that's what significant figures does. For all of these, the uncertainty, the plus or minus, it's approximately 5 feet, that sort of uncertainty, that plus or minus, that's always built into this last digit. That last digit, whatever the last number is never exactly that. It could be a little bit over, it could be a little bit under. Usually we don't know if it's one or the other. But it's always going to be baked into that last number. So our scientific numbers get reported so that every digit is certain except for the last. So in this 45.872, that 2 at the end It could be slightly higher than 2. It could be like maybe there's a 1 after here in reality, like that's the actual measurement. It could also be that it's actually 1.9 or something, or 1.8 or 1.7. But it's close enough to that 2 that we rounded it up, we rounded it down. In some instances, our measurements just aren't precise enough to say it's for certain this number. And we'll see how this plays out in lab this week. These first 4 numbers, however, we know for sure that it's 45.87. We're just not sure about that last little bit of information. That's how all of our numbers work anytime we measure something. The greater the precision of the measurement, so precision we're talking about like how small our measuring tool is basically. Like if you measure something on a yardstick, 3 feet, there's a lot of uncertainty within that measurement. If you measure something with a measuring tape, you pull it out, it's going to have feet, it's going to have inches, it's going to have maybe 1/16 of an inch. You're going to get a lot more precise measurement off of that. You're going to have to do a little bit less eyeballing. You'll be able to say, yeah, it's 2 feet 6 inches and 3/4 of an inch, something like that. You'll get a much tighter measurement with a measuring tape versus like a yardstick, assuming it's just 1 yard. And we'd also be able to report a greater number of digits. So looking at certain and estimated using a nickel as our example, again, we've got a blown up ruler here on the screen with centimeters on it. I added in a little red line here on the edge of our nickel just so that we can see where the nickel ends. It's lined up so that the left edge is on the 0. And if we were to measure where it is based on this red line, it's definitely past the 2. Right? Nobody would dispute that it's before the 2. It's definitely past the 2. We're certain about that. So that's why our 2 is certain. It's also past, the next markings are in 0.1s. So it's definitely past. That marking would be 2.1 centimeters. The next one would be 2.2 centimeters. It's between those 2 numbers. So it's definitely past this 2.1 centimeters. It is not to the 2.2 centimeters. So we lock in 2.1 centimeters. And then we guess. So anytime that we're making like a visual estimation, we don't just have something giving us the number. We get to make a guess. So thanks to the power of technology, we can zoom in on that. So how far are we from this 2.1 to this 2.2 on a scale of 0 to 10? Are we none of the way there? Are we all the way there? Or are we somewhere in between? Somewhere in between. Are we halfway there? Are we a little less than halfway there? A little less than halfway there. Maybe 2.2, 2.3, 2.4, somewhere in there. Those would all be reasonable guesses here. And that's what they are. It's just a guess. So the estimate that I put down was 2.12, but you might take a look at this and say that it's 2.13 or that it's 2.14. And so that's where the uncertainty element comes in, is in that last digit. We know, we would all agree it's past the 2.1. It's just that next measurement out that we would not be quite sure about. So we're going to estimate for these ones where we're not just told what the number is, 1 extra decimal place. And this works for metric, which is what we're going to be using for the class. If you try to do it with like inches, it gets really weird, and it's not fun at all. This isn't especially fun, but it's a lot nicer than doing it with like 1/16 of an inch and estimating between 1/16 of an inch markings. It's a nightmare. Any questions about that? All right, other places, other examples. This balance, this mass measuring device, this weight measuring device, has markings every 1 kilogram. That's the smallest unit, so we're going to estimate one place further from 1 kilogram. So 1 kilogram is the smallest mark. So we're going to estimate to the 10th place. I don't know why that one's so thick. I had a lot of fun finding pictures for this. This was like the one picture that didn't have just like somebody's bare feet standing on a scale. They had socks on. Thank you, whoever you are, for wearing socks when you took this picture. Because I didn't want to expose you to random strangers' feet. I thought that was weird. All right, so we've got on the scale our 115, our 120. And we've got measurement markings in between. So this mark would be 116. This mark would be 117. We're somewhere in between 117 and 118. We are definitely past 117. Right, the red line here is a little bit to the right of that 117 mark. And then we would estimate on a scale of 0 to 10, how far are we past that 117? And I came up with 0.2. You might see 0.1, you might see 0.3, you might see 0.5. If you said 0.7, you're crazy, you're wrong. But any of those lower numbers, that would be a perfectly fine guess. And usually I'll have you compare with people when you're making measurements in lab. You'll compare with your lab partner. We also have other things like this analytical balance, measuring this absolute brick of a phone. This is a 4-arm beam balance. I've got a 3-arm one in my office if you want to come see it. The way that these tools work is you've got a bunch of different slides for weight measurements. If you're a little bit on the older side, or if you have really good memory and you've been to the doctor, you might remember they used to do they used to check your weight with measurements like this. Or if you're going to a doctor that's got old tools. So this scale, we've got our hundredths place, it's set to the 100. We've got our tenths place, we've got our ones place, we've got our tenths place. So we can read them from back to front. We've got 100, add 30. We don't have anything in the ones place, so we've got 130. And then zooming up to our front measurement, we're past the 0.5. We are not to the 0.6. So 130.5, and we're at the smallest marking past that, so it would be 0.51. That's the 0.51 marking, and to my eye, it looked like we were right on that, and so we would say it's 0 out of 10, past that, it's right on it, so we add a 0. So sometimes the correct guess is 0, but you do need to make sure that you report that 0. If you don't report that 0, it looks like you made a measurement with a less precise tool. So we want to make sure that we include that 0. So these first 5 numbers are certain. This one's uncertain. Some of you may have looked at this. If you got to look at it in person, you might have said, I think it's actually a little bit past. You might have said 0.511 instead of 510. And it's generally known and accepted that there's going to be that guess at the end, and so scientists will know there's a little bit of plus or minus there, and the rest of those numbers are certain. All right, so let's pretend that you're staying in a cabin in the mountains during the winter. Must be nice being in a cabin, must be nice being winter. And you want to figure out how much to bundle up before going outside. You've got this outdoor thermometer. You look at it, and it's got this reading on it. The needle is pointed there. Please record the temperature reading to the correct number of digits. So do your best guess on what that number is. Maybe compare with your neighbor. And if you've got different numbers, maybe you can fight about it a little. I'll give you like a minute or two. All right, coming back after about a minute or two. So as I mentioned in the class on our break, on our work time, usually for making measurements like this, we want to look at what we're definitely past and what we're not quite past, whatever those smallest numbers are, whatever those smallest tick marks are. We figure out what those numbers are, and then we guess the distance between. So on this temperature reading, we've got our 0 is here. We've got our -10. So we're in negative numbers. So we're going to be counting from the 0 to the left. So we're 1, 2, 3, 4, 5, 6, 7. -7 is right there. And that's degrees Celsius. -8 degrees Celsius right next to it. We are somewhere in between those two numbers. So we are definitely at -7, and then we would have to guess how far we are between that. To me, it looks like we're definitely past halfway. We're maybe a little bit past, so I would say -7.6 or -7.7. How do we feel about that? You might even say 5 or 8. So something like that. Questions about making these types of measurements. We'll be doing these for a lot of our labs. All right, now to get on to significant figures. We've got some rules. There's a lot of rules in chemistry. We've got a lot of these lists, these check-down lists. For the most part, significant figures, I think, is just you have to practice it. Once you've got it down, then it starts to feel a lot better. Until you've got it down, though, it's going to be a little bit confusing. So we've got some rules that we're going to go through here. So we are talking about significant figures, which is often shortened to sig figs, which I often shorten even further to SF. SF just being sig figs, not San Francisco, go Giants, go 49ers. So our first rule is all non-zero digits are significant. So 1, 2, 3, all the way up to 9, any of those numbers, they're always significant. So we've got our 1, our 5, our 1s. Those are definitely significant figures. And then that's like the easiest part. Then we've got a bunch of different cases with zeros. So interior zeros between two numbers, are also significant. So we've got some zeros here. All those zeros are interior. Those are also significant figures. So if it's between two numbers that are significant, those zeros are significant. We also have trailing zeros, zeros to the right of a non-zero number. These are sometimes significant. The case where they are significant is if there's a written decimal point. So all of these zeros, because we have a written decimal point, those zeros are significant. You might be asking yourself, when are zeros not significant? And the when zeros are not significant is sometimes if there's an implied decimal point. So for these numbers, 50,000 and 10, we didn't write in the decimal point. So there's no written decimal point. So it's not clear if all of these zeros are significant, if two of them are significant, or if none of them are significant. The way that we remove that ambiguity, that we make it clear how many are significant, is we write it in scientific notation. So the safest way to avoid these trailing zero issues is using scientific notation. You don't always have to use it, but it can be helpful. So as an example, 350, the 3 and the 5 are definitely significant, right, because they're non-zero numbers. And we are not sure about this 0. So it could be just two significant figures with the 3 and the 5, or it could be three significant figures if the 0 is significant. If we write it in scientific notation, that helps us avoid that confusion. So for example, 3.5, times 10 to the 2. We only have two numbers there now, right? Our 3 and our 5. Those are both significant, so we've got two significant figures. For 3.50, we've got our written decimal point now. And so that 0 is significant. So this would be the way that we would show the difference between these two. And this is often a point where people will get a little bit confused because you'll write down a number 350, that's like a measurement that you got, or just anything with a trailing 0, and you'll forget that other people seeing that 0 aren't going to know if it's significant or not. It depends on the measurement that we're making. So like, if we had something that measured to the tens place, that's how we got this 350, and we guessed that it was 0, that 0, because we guessed it, that 0 is significant, so then we would write the 3.50. It could also be possible that we've got something that measures in hundreds, and we guessed that it was halfway between 300 and 400, so then only this 5 would be like something that we made in the measurement, so that 0 wouldn't be significant. So it depends on the situation. Significant figures, especially early on in the class, are things I'm happy to help you out with in labs. That's where we'll get the most experience, the most practice with our significant figures. They will also show up on exam 1. Another place where zeros are not significant is leading zeros. So zeros to the left of the first non-zero number are not significant. They just show us where the decimal is. You still have to write them. It's still important that you write them, the zeros in front, but they don't count for significant figures. So these 4 zeros in front or the 2 zeros in front. The way that I like to show that those zeros aren't significant, if I have $15, which is a small enough number that it's believable, would I ever write out that I've got $15 like that? Have you ever seen that in your life? No, right? We don't write those front zeros because we know where the decimal is. We would just write it as 15 instead of 0015. Otherwise, we could add as many zeros to the front as we wanted to, and it would look really ridiculous. Let me cross this out in different color. Right, so we wouldn't write those front zeros. They're not significant. That's why we leave them off. The reason that we include them for these numbers that are smaller than 1 is so that we know how small the number is. If you leave those off, it makes the number different. Same thing applies for these big numbers. If you cut off those zeros at the end, then it becomes a different number, which would be great if we could do that with, like, credit card debt or whatever. Unfortunately, world doesn't work that way. We have to include those zeros. But if we want to show for significant figures, then writing it in scientific notation is the best way to do that. So this is all applying to things that aren't exact numbers, things where we have to make some sort of a measurement. Exact numbers are things like our nickels from earlier. These, the way that we think about them, or the way that they sort of work, is that they have an unlimited number of significant figures. And the reason that this is important is because we're going to be thinking about significant figures when we're doing calculations. Another way that we can think about it for exact numbers is that they don't affect the significant figures of a calculation. So if we have an exact number, we can kind of just ignore the significant figures for that number. We just kind of pretend like it's not playing the significant figures game. So for exact counting of discrete objects, which is things like nickels, people, stuff that's got clear boundaries, dollar bills, even if you rip the corner off a dollar bill, it's still worth $1. So if you can count it on your fingers or just any number like that, that's going to count. Integral numbers that are part of an equation, so like for diameter the diameter is 2 times the radius. That 2 is going to be an integral number that's part of an equation. That's got an exact number of significant figures, so we can kind of just use it, but ignore the significant figures part. Some defined quantities, so things that are like the definition of, for example, an inch and a centimeter, those have an exact relationship to each other. And some of our conversion factors are going to do that and some are not. There's 2.54 centimeters in 1 inch. Those are based on each other. So the definition of an inch is that it's 2.54 centimeters or the other way around. So that would also be an exact scenario. On your yellow sheet, I think, on one of the sides, it has some conversion factors. I think some of those it says they're exact or not. Do we have any questions about significant figures, measurements, exact numbers? All right, more fun. Let's practice. Given these numbers, we want to figure out how many significant figures are in each number. We didn't take the measurements ourselves, so we don't know for sure. These are just measurements that somebody else took. We want to figure out how many significant figures they have. So 5.87, how many significant figures or significant numbers do we have in that number? We have all non-zero numbers. So we have 3 significant figures. In B, we have 2 non-zero numbers, and we've got leading zeros. Leading zeros are not significant. So this one has 2 significant figures. For C, 52.90, we again have 3 non-zero numbers, 3 New Zealand numbers, and we have a 0. This 0 is trailing, and we have a written decimal point. What does that mean? Is it significant or not significant? It is significant. So we have 1 significant 0. So we have 4 significant figures for C. We've got a combination of types of zeros in D. So we've got our 2 non-zero numbers. Those are the easy ones. So 2 non-zero numbers, so we definitely have at least 2 significant figures. And then we have to assess, what about these other zeros? So we've got leading zeros. Those are not significant. The slash through to show that it's a 0. Leading zeros, not significant. And we've got interior zeros. We'll do those in orange. Go Tigers. So we've got 2 interior zeros. Are interior zeros significant or not significant? They are significant. So interior zeros are, the 2 interior zeros are significant. So we've got our 2 non-zero numbers. We've got our 2 significant zeros. So we've got 4 significant figures. Separate these out. All right, and then 500. How many significant figures do we have in the number 500? We've got a 5. That's a non-zero number. So that one's significant. What about our zeros? We've got 2 zeros. Our options are none of them are significant, one of them is significant, both of them are significant. This one's a little bit of a trick. We don't have a written decimal point. So the trailing zeros are ambiguous. It's not clear. So the trailing zeros are ambiguous, not clear if significant. So we've got at least one, maybe 2 or 3 significant figures. So if this was a measurement that we took in lab, then we would want to make sure that we wrote it in scientific notation so that it was clear whether it was 1, 2, or 3 significant figures. And then how about this last one, 6 atoms? How many significant figures? We've got to guess for 1. Can you count atoms? Not like you personally, but could someone possibly count atoms? What if we replaced it with apples, 6 apples? You can count apples. What if they're different sized apples? Does that change the number of apples we have? What if they're different colored apples? Does that change the number of apples we have? Would anyone say we've got 6.1 apples because one of them's big? No. So this one's also sort of a trick. Infinite sig figs. Because it's countable. So sort of like counting the students in the class, counting the number of nickels, counting the number of dollars in our wallet, frowning at the void, the absence of dollars in our wallet. 0 is still countable, sort of. That's a math debate, probably. Questions about any of those examples for significant figures? All right, we've all mastered it. Now to move on to some fun stuff. So significant figures get used in calculations, and this is the part that drives students crazy in lab. When numbers get used in a calculation, so plus, minus, divide, multiply, stuff like that, the result is rounded up or down to reflect the number of significant figures of the data or of the measurements. And we've got rules for this. I mentioned we have a lot of rules. When we've got multiple steps, anytime that we've got multiple steps, we want to round only the final answer. The reason that we round only the final answer is if you do a calculation like 3.14 times 1.56, if you plug that into your calculator, it'll give you a number out. In this case, that number that the calculator gives us, 4.8984. if I have to do another calculation with that, so if I take that 4.8984, and I multiply that by 2.56, I will get in my calculator 12.539904. That's all the numbers that it told me. And then I could round this number. In this case, we don't know the rules yet, but I would round it to 12.5. However, if I rounded off this first calculation, we'll do a little bit more of an egregious rounding. Let's say that we rounded it to 5. And we do 5 times 2.56. Let's see what the number that we get is. Hopefully it's different. We get exactly, in the calculator, 12.8. Is 12.5 the same as 12.8? It is not the same. So oftentimes, if we round off our number, in this case it was a little bit of an egregious rounding issue, we rounded it up to 5. If you round it off before you get to your final step, you will get a different final answer. And this gets especially bad the more steps that you add on and the more times that you round it off. So I'll show you the way that I keep track of my significant figures when I'm doing multi-step calculations, but you could also figure out your own thing. Some important information for our labs. Every number that goes into a data table, the data table's looking something like this. Usually it'll tell you in this left column what the thing that you're putting in is, and then you put your number into this part. So let's say that we took this 12.539 and so on. When we put it into our data table, let's do the other number, actually, this 4.89. 4.894, let's say that that's what we get for our first thing. We would round this. We'd put the rounded number into our data table. You might keep track of the unrounded number outside of the data table, but the numbers that go in are always going to be the rounded numbers. Then we go on and do this calculation. We do the times 2.56. We take the whole number, the 4.8984, we multiply that by 2.56 to get the 12.5 that we put in our data table. So always using all of the numbers that our calculator gives us. If we're writing out our calculations, that means we're writing out all of the numbers that our calculator gave us. It doesn't feel great to do. It feels like, wow, what a waste of time. Once you get used to doing it, it's not that big of a deal. I do it all the time, as you will see throughout the rest of the course. So we want to use those unrounded numbers to avoid rounding errors. All right, we will cover, let's talk about multiplication and division, and then we'll take our midday break. So the result, the thing that we get out from doing multiplication or division, carries the same number of significant figures as the factor with the fewest significant figures. So the numbers that we put in determine the number of significant figures that we get out, and we're looking for the one with the fewest, the smallest number of significant figures. So we've got two examples up here. We've got the numbers 5.02, 89.665, 0.10. If you put those in your calculator, you'll get this 45-ish number. And we're going to round that. Round to how many significant figures? That's the big question. So we want to look at the numbers that we used to get that number. So those are this 5 and the 89 and the 0.1. How many significant figures does 5.02 have? 3. We've got our non-zero numbers. We've got an interior 0. So we've got 3 sig figs. For 89.665, those are all non-zero numbers. They're all significant. We've got 5 significant figures. For 0.10, we've got our 1 non-zero number. We have a trailing 0 with a written decimal point. And we have a leading 0. The leading 0 is not significant. So we have 2 significant figures. And so we pick 2 significant figures for the amount that we're going to round to. So this 45 and change number, we round to 2 significant figures. We count from the left over. So 1, 2, we're going to round at the 5. So 45. And the way that I would usually write this, I put a little line under the 5. That's our last significant figure. And we're looking at the next number, and only the next number, that 0, to see how we round. 0 is less than 5, and so we just drop everything. So 45. For division, the rule is the same. Multiplication and division are the same rule. So we've got 4 significant figures, 4 non-zero numbers. We've got 3 significant figures. We pick the smaller of those 2. So we're using 3 significant figures. So in the result that our calculator gives us, the 9, the 6, the 5 is our 3rd significant figure. That's our last significant figure. We look at the 9 to see how we round. 9 is bigger than 5, so we round up. 0.966 would be our number. So those are the basic rules for multiplication and division, and we'll take a 10-minute break. All right, coming back from our break, we talked about multiplication and division and mentioned rounding. Some of you may have forgotten how rounding works, so we're going to talk about it. For rounding, we're only going to look at the first number that we drop, the first number after our last significant figure, to decide how we're going to round. We can ignore everything else. We're going to round down. Which is dropping or turning into a 0 if that first digit dropped, is 4 or less. We'll round up if that first digit dropped is 5 or more. And again, we're rounding only the final answer. We're not going to round our intermediate answers. So some examples to round for 2 significant figures. 2.33. The first 3 is our last significant figure. We look at the second 3 to see how we round. 3 rounds down. That's going to round to 2.3. So we just drop that second 3 and everything that might follow it if we had more things there. For 2.37, 3 is still our second significant figure. We're going to look at that 7 to see how we round. 7 is 5 or higher. So it rounds this 3 up to 2.4. If we round the number 198.67 to 2 significant figures, the 9 is our last significant figure. The 8 is the first number that we would drop. So we're going to look at this 8 to see how we round. The 8 is bigger than 5, so it tells us we're going to round this 9 up. What's 1 bigger than 9? What number is bigger than 9 by one number? If we're counting on our fingers, we've got one finger left. What's that last finger? What are we counting? 10. 9 rounds up to 10. And that, because this is a 10, so we'll do it in a different color. So it turns into 10. And we already have that 1 there. 1 plus 1 is 2. So this 1 turns into a 2, and we have a 0 now in this spot. So we get 200, we drop all this other stuff. The issue that we would have with this number is that it's ambiguous about how many significant figures. We know that it's 2 significant figures. We need to show that, and so we would turn this into scientific notation, 2.0 times 10 to the 2. A common mistake that happens here is we feel really uncomfortable turning that 9 into a 10. That's just the way the numbers work. It's okay. We can do it. I felt really uncomfortable about it too when I was in your position. We can turn that 9 into a 10. It's no big deal. We would just make sure that we put a 0 there and add that 1 to the next place to the left. Another common mistake is that people would drop the 0. So it's not going to just be 20. It's a completely different number. 20 is a very different number than 200. If your friend owes you $200 and they say, well, that's the same as 20, you would say, no, no, no. That's $180 different. You will be paying me the $200 that you owe me. Or you just say, what's $200 among friends? But more likely than not, you're going to be getting your $200. So that's rounding. So let's do some more examples. We want to perform these calculations to the correct number of significant figures. So we've got 5 significant figures. For both of these numbers, very convenient. So we just have to put it into our calculator. The number that our calculator gives us is this, 2085.5688. We want to round this for 5 significant figures. So we count from the left. 1, 2, 3, 4, 5. The second 5 here, that is our 5th number, our last significant figure, since we only have 5 significant figures. We look at the next place over, that's the 6, to see how we're going to round. 6 is 5 or greater, so we're going to round up. So our number, 2085.6. For B, we've got 125, which is 3 significant figures. We've got 9.0000, which has 4 significant figures. So we are going to have how many significant figures in our answer? 3 or 4? 3. We pick the smaller number. So 3 significant figures. So 125 times 9 into the calculator. That's a number 1125. We want to round this for 3 significant figures. We count from the left. The 1, the 2 is our 3rd significant figure. look at the 5 to see how we round. 5 is 5 or greater, so we round up. So 1130. How do we feel about that? We have a trailing 0. Do we have a written decimal point? We don't have a written decimal point. So this 0 is ambiguous. We know from our 1125, the 2, the tens place, that's our last significant figure. So we need to write this in a way, this 1130, we need to write it in a way that shows that 0 is not significant. How can we do that? What's a different way that we can write a number? Scientific notation, perfect. So we're going to put this into scientific notation. We move the decimal place over. We want our decimal place to be after our first number. So our decimal part is going to be 1.13. We only write the numbers that are significant, so we're stopping at the 3, no 0 there. And the number of places that we would have moved it over to get there are 3. So 1.13 times 10, we moved it over 3 places. Is it a big number, positive 3, or is it a small number, negative 3? What are we writing in? Is 1,130 a big number or a small number? It's a big number, so we're going to write positive 3. Questions about multiplication, division? This is arguably the easier of the two types of operators. We also have addition and subtraction. And addition and subtraction have a different rule. So for multiplication and division, we care about number of sig figs. Sig figs are what are important, the number of significant figures that we put in. The smaller of those is the number of significant figures that we get out. For addition and subtraction, we care about decimal places. DP here is decimal places, not Dr. Pepper. We also care about Dr. Pepper, but decimal places is what we're talking about in this case. So in addition and subtraction, the result, what we get out, carries the same number of decimal places. Same number of decimal places as the fewest decimal places. This is really easy if we line it up to do it by hand. So in these examples, we've got it all lined up. So we don't care about the number of significant figures. We care about what's the least precise decimal place. Usually, it's places after the decimal. So we've got, for 5.74, 2 decimal places. 0.83 has 3 decimal places. Our answer, we also have another number, sorry. Our answer is going to have the smallest one, 2 decimal places. And we can see that if we draw in a little line. So we're going to cut everything off that's to the right of that line. So 5.74 plus 0.823 plus 2.651. Calculator says 9.214. And we chop off that 4. So the 1 is our last significant place. We look at the 4. Since 4 is less than 5. This rounds down to 9.21 final answer. So that this has 2 decimal places, just like our 5.74. For 4.8 minus 3.965, we've got 1 place after the decimal and 3 places after the decimal. So our answer is going to have 1 decimal place. Or if we wanted to draw a line through, we draw a line in after that 8. 4.8 minus that 3 number. Calculator says 0.835. The 8 is our last significant number. We look at the 3 to see how we round, and we would round down to 0.8. So for multiplication division, we care about number of significant figures. For addition subtraction, what we're doing here, we care about number of decimal places. Another thing that can happen in addition and subtraction is that we might end up with a very different number of significant figures once we're done with the calculation. That can also trip people up. So 28.02 minus 27.99. We're doing addition subtraction, so we care about decimal places. These both have 2 places after the decimal, 2 numbers after the decimal. So we are also going to have 2 numbers after the decimal for our answer. And the number that we would get out is 0.03. And suddenly all of our beautiful, big, precious significant figures have disappeared, and we only have 1 significant figure. That happens from time to time. This is a little bit of an extreme example, but we will almost definitely have people see this happen in their labs if we're doing addition subtraction. You can also gain significant figures when you're doing addition subtraction. That'll likely also happen. Questions about addition subtraction? All right, now that we've mastered multiplication, division, and addition, subtraction, significant figures rules, oh, just kidding, we've got some more examples. But as you might have heard, we're going to combine them. Sometimes we do both at the same time. And that also gets a little bit hairy. We'll get the best practice with significant figures when we're actually in lab. So you can look forward to that tomorrow. All right, we want to perform these calculations to the correct number of significant figures. I'll give you a little bit of time to try the first one, and we'll go over the second one together. I'll go ahead and write in what the calculator gives us. Now we're working with addition, subtraction. What are we looking at? What do we care about for significant figures? Do we care about significant figures? Do we care about decimal places? We care about decimal places. So we're going to look and see. We've got 2 decimal places. We've got 3 decimal places. Which one are we going to pick for our answer? 2 decimal places. It's the worst one. We have to go with the worst one. So 2 decimal places, that means we are looking at the third 9. That'll be our last spot. We take a peek at the 6 to see how we round. How are we going to round, up or down? Up. And when we round 9 up, what does it turn into? 10. So that's going to affect the number next to it, which is also a 9. So that's going to turn into a what? Also a 10. So this rounds all the way up to 922. And we need to keep those decimal places in there. So 922.00. Questions? For B, we are again, since we're still doing addition subtraction, we're caring about our decimal places. We've got no places after the decimal, no places after the decimal, 2 places after the decimal. We're going to pick no places. So we look at our 1. That's our last significant place, our last significant figure. The 0 tells us just keep it the same. So 2001 is our answer. Just a reminder, this is a place for learning. This is a place for making mistakes. So if you have questions, feel free to ask. Yes?
Why wouldn't we turn it into scientific notation?
Which one?
Since they're whole numbers? Or like,
So we don't have to turn either of these into scientific notation. The 2001, because our last number is a non-zero number, and our interior zeros are always significant. For 922.00, we have a written decimal place. This written decimal point, means the zeros after it are significant. So that's why we don't have to put them in scientific notation. That answer your question? Cool. Any other questions? You could always, if you wanted to, choose to just write every number in scientific notation. That's a choice that you can make. It's a little bit annoying for me to grade, but I don't really mind. I'm good at scientific notation. I'm just not used to seeing them all in scientific notation. Okay. Now, combining addition, subtraction, multiplication, division. We are going to abide by PEMDAS. In case you forgot, PEMDAS, please excuse my dear Aunt Sally or whatever other mnemonic device you might have heard. We are doing steps in parentheses first. We don't really do a lot of exponents, but we would do exponents next. And then we would do multiplication, division, and last we would do addition, subtraction. This is just the rules for how we do our calculations. So if we've got a combination of things, we're going to do whatever's in parentheses, even if it's addition, subtraction, we're going to do that first. The parentheses say start here. Then, once we've done everything that's in parentheses, then we can do multiplication, division. Finally, we do addition, subtraction. Your calculator does this perfectly. Sometimes that is not to your benefit because you forgot to put it in so that your calculator does it perfectly. So we'll run into some of those issues, I'm sure, during the course. It's not a big deal. Calculators can be confusing. Another important part is we're going to get intermediate answers without rounding. We're going to only round the final number. Since we're doing multiple steps, this is where it becomes increasingly important that we keep track of our significant figures. I like that little red underline or whatever color underline to keep track of where my significant figures are. So I'll show you what that looks like. So we've got some mixed operations. We've got some extraneous, unnecessary parentheses. We've got 2 times, secretly there's a times there, 2 times 1.008 grams plus 15.99 grams. Keeping in mind PEMDAS, we're not doing anything inside the parentheses. The parentheses is just keeping that number separate from the 2. So we can skip that. We don't have any exponents, so we're going to multiplication division. So we're going to do 2 times 1.008. This 2 is probably exact. Probably, but not definitely. So we would put into our calculator 2 times 1.008, 2.016. Keep the units on there. We had 4 significant figures for 1.008, so we're going to have 4 significant figures for 2.016. We'll put a line under the 6 just to keep track of things. It's probably not necessary. This is assuming that 2 is exact. We'll look at what if it's not exact. Then we are going to add 2.016 and 15.99. So we were doing multiplication. We cared about significant figures, number of significant figures. Now we care about what when we're doing addition? Decimals. How many decimal places do we have in 2.016? We've got 3. And how about 15.99? 2. So our answer is going to have 2 decimal places. So our answer will be something with 2 decimal places. 2.016 plus 15.99. The number we get out, 18.006. We want to round it for 2 decimal places. So the second 0 is our second decimal place. We look at the 6, we're going to round up. So this would be 18.01 grams, or G. We want to make sure that we're including our units when we have them. So that's assuming that the 2 is exact. If the 2 is not exact, because I forgot what I meant to do here when I made this problem. So if the 2 is not exact, 2 has 1 significant figure times 1.008 grams. That still turns into 2.016 grams, but we would only have 1 significant figure. So that 2 would be our last significant figure. Then we do the 2.016 grams plus 15.99 grams. How many decimal places? How many significant decimal places do we have in 2.016 now?
3.
It's not 3. It's not 4. It's not 2. It's 0. It's 0 because this 2 is our last significant figure. We have 0 places after that decimal that are significant. That's why we include this little line. So this one is actually 0 decimal places, 2 decimal places. The smaller of those is 0. It still comes out in our calculator, should still come out to the same number, 18.006. The difference is how we round. So 0 decimal places, that means that 8 is our last significant figure. So it would be 18 grams. Question?
How would we know if the 2 is not exact?
If it was from an equation, then the 2 would probably be exact. Usually in equations, if it's a whole number, it's an exact number. I can't think of a scenario where we would have this specific combination. Maybe we had 2 items that, no, that would be exact. I can't think of a scenario where it wouldn't be exact. So it would probably be exact. It's just more interesting to show the not exact, because then we get that like the 0, 1, 6 doesn't matter sort of thing. All right, we'll be assuming that the 2 is exact. We'll just assume that all these 2's are exact. In B, what are we doing first here? Parentheses. We've got just a number in parentheses, so we don't have to do anything with that. What do we do next? Multiply. What are we multiplying? We're multiplying 2 and 35.45 seconds. 35.45 has 4 significant figures. 2 is exact, so it doesn't factor in. We're going to have 4 significant figures. So we get 70.90 seconds with 4 significant figures. And we've got our 137.3 seconds. We're going to add to that. What do we care about for addition? Decimal places. How many decimal places does our first number have? 1. 1 decimal place. It's just the 3. And how about our second number? 2 decimal places. So we're going to pick for our answer how many decimal places? 1 decimal place for our answer. So 137.3 plus 70.90, 208.2 is what our calculator tells us. Is that the correct number of decimal places? It is. Perfect. So that's our answer, 208.2. Last one, we've got C, but in italics. We've got 118.7 grams divided by 2 minus 35.5 grams. We're going to do the division first. So 118.7 divided by 2, 59.35 grams. That's going to be 4 significant figures because 118.7 grams also had 4 significant figures. Subtract 35.5 grams. We've got 2 decimal places. We've got 1 decimal place, so we're going to pick 1 decimal place for our answer. Calculator gives us 23.85, and we keep the grams on there. So which of these four numbers is our last significant figure? 2, 3, 8, or 5? 8. 8 is our last significant figure. It's our first decimal place. We're going to look at the 5 to see how we round. 5 is 5 or greater. So we're going to round this up to 23.9. Keep the units grams. So that would be our final answer. Questions about any of those? All right, moving on. Chemistry, part of the reason I think that chemistry is difficult, there's a few reasons. One of them, lots of details. Lots of people don't like lots of details. I particularly enjoy lots of details. My brain seems to really like them. Another part of the reason that people don't like chemistry or chemistry is difficult is we do a lot of problem solving. And problem solving and critical thinking, not skills that everyone has practiced a lot, and so that makes chemistry a little bit more difficult. So we're not going to have simple formulas for all of our problems. There's a lot of different steps that we're going to learn. If you learn all the individual steps, you learn how to put them together, you can solve all the problems that we've got in chemistry, at least in this class, with relative ease. If you're trying to memorize whole solution maps at a time, that's going to make things a little bit more difficult. So we're not going to have simple formulas for every problem, but we can learn some problem-solving strategies. A lot of our problems are unit conversion problems. Many problems can be solved by the units. Just looking at the units that we have, the units that we want, you can put together a solution map. Sometimes it's one step, sometimes it's two. A lot of times the units can guide us to the correct answer and tell us how we need to multiply things. Other problems, we are going to use specific equations. Usually the first time they show up, you'll get them on your information sheet for the exam. So for converting between units, units behave just like algebra variables. So x times x, x squared, y squared divided by y is y. The same things work for inches and other units. Inches times inches, inches squared. If we've got grams per milliliter times milliliters, the milliliters would cancel, we'd get grams out. So a lot of the problems, if you're good with algebra and we think of our units as algebra variables, a lot of the problems you can solve just with some simple algebra. And this method, this using the units as our guide, is called dimensional analysis. The dimensions being the units themselves. So some things that we want to do. We always want to write every number with its unit. Write every, literally every unit. If there's a unit, we want to make sure that we're writing it down so that we don't forget it. Especially when we get to 3- and 4-step problems, if you leave off a unit or if you leave off 2 units, then that can screw up the numbers that you get out. It can screw up the units that you get out. You might get the wrong answer, or you might have set up your solution map incorrectly. We always want to include units in our calculations. That's part of the writing every unit. You'll see me do that throughout the duration of the course. Trust me, I don't need to. I could just plug the numbers into my calculator most of the time. I don't need to write it out because I've done these a billion times. This is to help us catch our mistakes. If I don't write out my units, I will sometimes make mistakes. If I work too quickly, even I will make mistakes. I've got over 500 hours of lecturing just on this class. I will still make mistakes if I don't write out all my units, if I don't write out all my numbers. So trust me, you will too. Probably, unless you're perfect. We also don't want to let our units magically appear or disappear. They need to cancel out to disappear. So by canceling out, meaning like up here with the grams over milliliters times milliliters, if we've got one on the top, one on the bottom, milliliters divided by milliliters, turns into a 1, it's gone. So we have to be able to show that it disappeared somewhere, or show that we got rid of it. For a lot of our conversion problems, we'll be given a quantity in some units, a number with units with it, and we'll be asked to convert that number, that's what a quantity is, to another unit. I usually color code my problems when I'm doing them for class. So if it's in green, that's something that we're given. If it's underlined or in that fuchsia color, that's what we're trying to find. And then a lot of times other things are in green, or sorry, in blue. So we'll have some information that we're given. We want to get to some other information, and we use conversion factors in between. We'll learn how to construct conversion factors in a moment. So the units that we're given, our conversion factor should have the units that were given in it, as well as the units that we want. We can cancel out the units that were given. Right, we've got given units on top, given units on bottom. This would be like the milliliters times grams per milliliter that we did earlier. I just switched the order. 1 milliliter on top, 1 milliliter on bottom. Those units cancel, and we would get the grams that we want, for example. We can make conversion factors. You will often have to make your own conversion factors. Any two things that are equal makes a conversion factor. So this is an example of a table. It's got a bunch of different units. We've got our English unit. We've got our metric unit. So the ones that we're used to using and the ones that the rest of the world is using. Any of these two things, if it's equal, which these are, we can make a conversion factor out of them. We can also use our prefixes, our kilo, our centi, our milli, our mega, our, those sort of things. We can use those as well. The way that a conversion factor works is, let's use this grams and ounces as our example. You put one on top, and you put the other one on the bottom. And if you want to, you can, for free at no charge, and with very little brain effort, switch the two. Just flip the top and bottom, and it's the same thing. It works exactly the same, but it's better for different units. So 1 ounce over 28.35 grams. These would be our two conversion factors. For ounces and grams. So anytime if you want to convert from ounces to grams or grams to ounces, you would use one of these. The math reason that these work is these two things are equal to each other. So they're essentially the same. 1 ounce is the same as 28.35 grams. So essentially, all this is, these are just ones. So we're not changing anything, we're just swapping our units out. That's the maths of why it works, which most of you probably could not possibly care less about. And that's fine. All right, construct some conversion factors for feet and inches. How many feet or how many inches are in a foot? 12. So 12 inches equals 1 foot. Please construct the two conversion factors for that. For inches and centimeters, 1 inch is equal to 2.54 centimeters. Please construct the two conversion factors for that. All right, so the magical way that we make conversion factors, the fast method is just put one on top, put the other one on the bottom. So 12 inches over 1 foot, or the opposite, 1 foot over 12 inches. Usually, you're only going to make one of these, because one of these works for one direction, the other one works for the opposite direction. So if we're converting, let's pretend like I'm 2 inches taller than I am. I'm 6 feet tall in pretend world. I'm not actually 6 feet tall. But let's say we wanted to figure out how many inches tall I am because I'm filling out some, BuzzFeed questionnaire or something. I'm starting with 6 feet and I want to know how many inches tall I am. Lots of us would probably just ask Google to do it for us, but it's important that we know how to do it for ourselves. So 6 feet, 2 inches. We want to select the conversion factor that's got feet on the bottom to cancel out the feet that we have. So we would be using this 12 inches over 1 foot. 12 inches over 1 foot. I'm probably jumping the gun a little bit here, but those feet would cancel out, and we would plug into our calculator 6 times 12 for 72 inches. Just showing us, like, this is where we would use this. This is how we might use this. For our conversion between inches and centimeters, our two conversion factors are going to be 1 inch over 2.54 centimeters and 2.54 centimeters over 1 inch, or divided by 1 inch. Questions about getting those? The actual maths of how we would do it, we'd be dividing both sides by one of those things. So for this example with inches and feet, we divided both sides by inches, and then we've got 12 inches over 12 inches, that's equal to 1. So 1 equals 1 foot over 12 inches. And the 1 foot over 12 inches is the part that we care about. That's our conversion factor. You don't ever have to show me to do that, how you did that. You can just put one on top of the other, and I understand what happened. All right, so when we're converting between units, when we're doing problem solving, we want to check that the final units are correct. Sometimes if you set a problem up incorrectly, you'll end up with what I call crazy units, units that you've never seen in your entire life, and you hopefully will never see in your entire life. Things like inches, grams per cubic centimeter. Things that nobody's going to ever use. There's no reason to have them. And it doesn't look like anything that makes any sense. So you want to make sure that the way you've set your calculations up, that your final units are correct. And if you set up a solution map, if you set up your calculation, we can check that our units cancel out before we put anything into our calculator. Which is one helpful thing of writing everything out. So if you write out your whole calculation and you look through and you're canceling out your units and you say, ooh, I didn't cancel these units out correctly, it's possible. The likely thing that happened is one of your conversion factors was just the wrong way. You flip it. You go through and check your units again. Okay, we got the correct units out. Perfect. Now I can plug it into my calculator and we'll get the right answer. So we want to make sure that our units are correct when we're solving problems. We also want to check that the magnitude pop of the answer makes sense. The size of the answer is reasonable. For a lot of these, you're not going to have a good sense of whether the size is entirely reasonable, unfortunately, just because you haven't worked with the numbers all that much. To give you an example, let's say that I'm converting my height. We'll just keep using my height as an example. I'm not obsessed with it. We'll use my height as an example. Let's say I'm converting my height from, we'll do inches to feet. So let's say that I know that I'm 70 inches tall. I set up my calculation, I plug the numbers in, and I get out that I am 840 feet tall. Does that seem reasonable? No, I'm definitely not 840 feet tall. That would be a nightmare. I wouldn't be able to fit into any cars. So that would be a warning sign. That's way too big for the height of a person. So we would know we did something wrong. Let's go back, check our calculations. Turns out I multiplied by 12 instead of dividing by 12 is what would have happened there. The more that we work with the units that we use in this class, the better sense that we'll have of whether the number that we're getting is correct or not. I've worked with them a lot more than most of you, I'm guessing, so I've got a better sense of when things are right or not. And I'll try to point out instances where I'm seeing that our units make sense or not. And as I said earlier, we can invert, flip top and bottom, our conversion factors, for free at no cost with very little brain power involved. So that can be helpful at times. We will also oftentimes be writing out a solution map. So a solution map is a visual outline just showing, usually the way that I do it is I show the units we start with, the units that we end with, and then we set up a couple of steps in between for the units that we're going to step to, so that we know how many steps we need to do, and then we can put in the numbers after that. So for our unit conversions, which a lot of our things are, our solution map is going to focus on the units. And that'll often, for a one-step problem, look something like this. So if we're converting from inches to centimeters, we'll start with inches on the left, centimeters on the right, and usually something like a blue arrow. In this case, we can do inches to centimeters in one step. So we would set that up, and then we would either know or go find our conversion factor and set that below. So this tells us we're going to take the number of inches that we got, we're going to multiply it by 2.54 centimeters over 1 inch, and that'll give us out centimeters. The opposite direction is shown below with centimeters to inches. Just to show you how serious I am about this, we've got even more slides about solution mapping and problem solving. So when we approach a problem, especially if it's something that we haven't seen before, we want to identify our given information. Stuff that we have to start with. We want to identify the endpoint, the find variable. This is usually next to a question word. Can somebody give me an example of a question word? A word that indicates you're about to ask a question or you're starting a question.
What?
A question word. I'm just kidding. You said what, so I said a question word because that's what I wanted you. All right. Yes, what, who, what, and where, why, how, all of those words. Usually, those words are right next to some unit or something that we're asked to find. So that's one way that we can identify what we're asked to find. And then the given information is usually going to have numbers. So we'll have some numbers, that's given information. We'll have something like a unit that's next to a question word. That's what we're looking for, that's our find. And then we devise our solution map. So we'll have some given unit. We'll have our find unit or our end unit. That's what the answer is asking for. And we'll set up maybe a couple of steps. Intermediate units. And we would write our conversion factors under those. You don't have to use these exact methods, but the idea is that we can build up some problem-solving strategies because a lot of the problems in chemistry can be or feel very daunting. They don't need to be as scary as they come off as. Here's another way of looking at it. So sorting our information, that's what we were talking about, our given and our find. We can strategize, create this solution map, something that looks like this. Doesn't have to be color-coded. I color-code it because it's free. And it makes it easier to do when we look back at it. And then we would set everything up, do the math, cancel our units, and then lastly, we might check and see that it makes sense. Like if I'm 840 feet tall, hey, that doesn't make sense. Let's go back and check our work. Do we have the correct units? If we don't, let's go back and check our work. Is the number of significant figures correct? If not, check our work. All right, one example, real quick. Convert 56.0 centimeters to inches. What is our given here? What are we given? 56.0 centimeters. What are we trying to get that to? Inches. It's about the simplest problem that we could possibly have. So we are going to start from centimeters for our solution map. We are going to go to inches. Can we do that in one step? Do we have something that relates centimeters and inches? The answer is yes. And your yellow sheet should have a conversion for this. The yellow and green sheets that were handed out today or that you hopefully picked up, those are for you to use as references in class as well as when you're working on the homework. You will not get to use your yellow and green sheets on the exam. Feel free to write on them though, whatever you want to know. You'll be given an information sheet that's blank, brand new, on the exam. So just a word about those. All right, what is our equivalency? What's equal to what in centimeters and inches? Who's got it? 2.54 centimeters equals 1 inch. We are starting with centimeters. We're trying to get to inches. Which of these two units do we want on top? Inches or centimeters? Yes, it's inches. We want inches on top. 1 inch. That's the number that's going to come out, or the unit that's going to come out. And to get rid of the centimeters that we started with, we want centimeters on the bottom. So our conversion factor, the one we'd want to use, 1 inch over 2.54 centimeters. Because it's free to flip conversion factors, if we set it up the opposite way. We check that things cancel out. They're not going to cancel out. We just flip it and check it again. Okay, so the way that I would write this out, 56.0 centimeters. And I like to draw a big line through everything to make it very clear where things are on the top, things that we're multiplying, and things are on the bottom, things that we're going to divide by. So we've got our given of 56.0 centimeters, this vertical line just letting us know we're separating things out. And we'd plug in our conversion factor, 1 inch over 2.54 centimeters. Put an equal sign at the end, and let's check our units. So we've got our centimeters from 56.0 centimeters on the top. We've got our centimeters from 2.54 centimeters on the bottom. We've got one on top, one on bottom. Those are going to cancel out. So our centimeters cancel. The only unit that's left is inches. So we can carry the inches over to the end. And then into our calculator we plug 56 divided by 2.54. Calculator says 22.047244. Got to move my inches back. Oof. 4409. Is that our final answer? It is not our final answer. What do we need to do? What do we need to think about, consider? Go Niners. I'm not actually a huge Niners fan, but where are the Niners from? 49ers. SF. What's SF stand for? San Francisco. In this class, though, it stands for significant figures. So we need to remember to do our significant figures. 56.0 has how many significant figures? We've got 2 non-zero numbers. We've got a written decimal point and a trailing 0. We've got 3 significant figures. And our conversion factor looks like it has 3, maybe. It's actually infinite. This is an exact conversion factor, so we are expecting 3 significant figures in our answer. So looking at our number 22.047 and so on, the 0 is our third number. We're going to look at the 4 to see how we round. 4 is less than 5. So we round down, and our answer would be 22.0 inches, final answer. Questions? Okay, then we will stop there for today.